Record anyway. All right, so I'm going to go back to the example that we had last week because we had one that was last Monday is where I left off, and we were doing two examples. The one with the conducting sphere, and now this one we're going to do with the dielectric sphere. So the idea is this: we have external field E naught. And in that field, we put a dielectric, constant epsilon, radius A,
Liz, we can hear your thing dinging, or someone's. And
it's all right.
Not muted.
Okay, so this is along the z-axis here. So when we take a point P out here somewhere, we would describe that as having coordinates r and theta with respect to the z-axis. And so now we want to write down the general forms inside and outside. So we're going to already exploit the fact that it's independent of the phi. And so we're not even going to worry about the phi. So inside we get this: the sum over AL R to the L PL cos theta from L equals 0 to infinity. And the reason why we don't see the other term there with the 1 over R to the L plus 1 is because this has to be finite at R equals 0. So therefore, we only get the set of coefficients multiplying the positive powers of R. Now on the outside, we get both. We'll have to adjust this for a second. So on the outside, we have the summation L equals 0 to infinity. This time it's B sub L R to the L plus C sub L R to the negative L plus 1 multiplied by PL cos theta. And normally we would say, well, these go to 0 here, but that's no longer our boundary condition at infinity. So in other words, when you place something in an external field, we assume that first of all, that external field is generated by charges that are far away from this, okay? In other words, I would generate an electric field, a uniform electric field with a parallel plate capacitor. All right, but if I have that parallel plate capacitor and I put the dielectric sphere in here, if my dielectric field looks like this, then I'm going to have a problem assuming that the electric field is uniform. If I did something like that, see what I mean? It's not going to. Oh, okay. So generally, when we're talking about those types of things, we'll do this. You say, okay, this is a little bit, or actually it's smaller than this, so that the external field is not really messed up by what's inside. All that is to say that as R goes to infinity, the phi out needs to match the potential of the field. And that potential of a uniform electric field in the z direction is minus E naught z, or minus E naught z or minus E naught R cos theta. This matches if B1 is equal to negative E naught and all other B are 0. So I'm going to come back over here and rewrite that. I'm going to write my phi in over here and my phi out over here too. So my phi in, sum L equals 0 to infinity, A sub L, R to the L, PL cos theta. And then my phi out is going to be my B1 term. Let me scoop this open. My phi out is going to be my B1 term, which is minus E naught R cos theta, plus the other terms that go ahead and go to 0 at infinity. So the sum over for L equals 0 to infinity of this CL divided by R to the L plus 1 multiplied by PL of cos theta. So that's just our general form for outside and inside. And now we have to apply the proper boundary conditions. Which for our dielectrics are a little different. So for our dielectrics, we know that the E parallel, or the tangent portion of E, is continuous. So I'll go ahead and say E tan. E tan is continuous. So at the surface, at little r equals capital R, or I'm sorry, little r equals A, when I plug that in, I need my tangent component of the electric field to be continuous. The tangent component here is the one in the theta direction. So I want the E theta and when I look at what that component is in terms of spherical coordinates, I get it's minus 1 over R partial of the potential with respect to theta. You could kind of suspect that the partial of phi with respect to theta would be in there, okay? The 1 over R comes from the fact that the theta is a unitless thing, and so the farther you go out, you're running a 1 over distance, so therefore it's 1 over R. Okay, so then what we write here is we match the inside and the outside. So I'm going to go ahead and evaluate this part at A, so 1 over A, okay, d phi in, d theta equals minus 1 over A, d phi out, d theta, when both of these are evaluated at R equals A. All right, so let's take a look at this. Do this. So I get minus 1 over A times, since the derivative is with respect to theta, I can go ahead and carry it inside of this thing. So I will. And what I get is I get some A sub L, A to the L, of d PL cos theta d theta. Equals, I'm going to run out of room. All right, hang on. I'm just going to rewrite this over a little bit, okay, so I can have room. You want room? All right, too big for my own good, apparently. Now that's the equal. Just look out here. So we're going to get one term from this. So so minus 1 over A, okay, minus E naught A. Go ahead and do this. dv theta of minus E naught A cos theta. In this case, I can plug the A's in before I take derivatives because I'm taking derivatives with respect to theta. So the R doesn't change, so I don't have to worry about that. And then I have the other part, which is a minus 1 over A times the sum of CL over A to the L plus 1 multiplied by D PL cos theta d theta. All right, so we got two cases here because all terms have to match up. So in other words, this has to be true for all theta. It must be true for all theta. All theta. So each DPL, okay, each of these must match with each of the ones over here. Now, the one thing to remember is that this right here is P1 of cosine theta. Okay, so we want to remember that because that'll be a little special case. So we'll take care of the A1 terms separate. So what I get out of this, so the 1 over A is in every factor, so don't need to worry about that. The A to the first power is in this factor. So the one terms look like this. I got A1, A, dP1, d theta, right here, equals, I'm multiplying out all the minus A's out here. So I got negative E naught A, dP1, d theta. And then I take the first one out of here. plus C1 over A squared dP1 d theta. So this has to be true for all theta, therefore the coefficients must match. I can divide through by A, and so what I get is I get this. A1 is equal to minus E naught plus C1 over A cubed. We have to do that one separate. So put this off to the side. Okay, so you got that off to the side. Make sure you get this off to the side because I'm going to start erasing because I got to do the rest of the L's. Okay. Any questions on how I got the first term? Basically, I just took the first sum out of each part of the thing, and by the way, I'm multiplying through by this factor, so I'm not worried about it. Okay. Okay.
Dr. Collins?
Yes.
So you're setting the summation of A sub L times little a to the L, take the derivative PL cosine theta, and
Yes.
you set that equal to the derivative in terms of theta negative.
So in other words, what happens is, since all of these L functions are linearly independent of each other, the coefficient of each of these derivatives must be the same on both sides of the equation. So for the first one, we have multiple derivatives, okay? So in other words, I'm going to rewrite this term right here. So watch. This is minus E naught A dP1 d theta plus this, okay? So the first term, so for L equals 1, I've got this extra term in here that I'm not going to have for any other L. That's why we have to treat it different.
Okay, so only for L equals 1, you get that.
There's going to be an extra term. Because for all the other ones, this is only 1. This isn't going to match up. This isn't going to do anything with any of the other L's. Okay? So let's put this up. I'm going to put this little information up here. So I know that A1 is minus E naught plus C1 over A cubed. So in other words, we're going to have to do like cases for all of these. All right? All right, so now when we look at L not equal to 1, okay? So for L not equal to 1, let's see what changes. Okay, well, first of all, these are L's and not 1s. These are L's and not 1s. L, 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 L. And this one isn't there because there's only a P1 with that one. Because that one isn't there. That's gone. So there we go. I know I kind of did that pretty quickly, but you see what happens if there is no, the E naught term isn't there. So for L not equal to 1, you just have this. So it looks the same except for there's no E naught. Okay? So A L equals CL over A cubed for all L not equal to 1. For L equals 1, we have that, and for L not equal to 1, we have this. Oh, I did that wrong, didn't I? Sorry. I can't divide right. I gotta fix that. This is A to the L. This is equal to CL divided by AL plus 1. There we go. I jumped the gun.
Oh, right.
So now I gotta let you guys catch up. So what's this divided by here? Well, I got A to the L, and I have to divide the A to the L over there, so what do I get? Michael, do you know what that is? So in other words, I'm taking this term, these things are dividing out. And now I just want to do this. What is that?
Isn't it?
Oh, I'll give you a hint. There's an A in it. Okay, there, good. So what is it?
Dr.
A
Collins?
to,
For just, well, it's not L plus 1.
no, because I have to get rid of this A to the L over here.
Oh, so it's just AL.
No, I'm dividing.
plus
I'm dividing this.
Right, so it's AL plus 1 and
Plus
then
plus
sub,
L.
and then-
L, which is what?
Oh, plus L, 2L. Sorry.
There we go.
2L plus.
Sorry about my writing. And I'm even trying to use this fancy, L here to distinguish it between, that and the 1 too. So this then is A to the 2L plus 1. So that goes over here. We want to check for consistency, we can here, because this coefficient should be the same as that if I plug L equal to 1 in here. And if I plug L equal to 1, 2 times 1 is 1, plus 1 is 3. There we go, I get A cubed. Okay? Cool, huh? Right? Yes? All right, so that's half the battle. That's half a bar thing. But now, you gotta do something else. Okay, you ready for me to erase? I'll start up here. All right, so because we don't really know about any kind of charge density, because we understand that there may be some polarization charge density that's going to cause a surface charge density or something like that with these epsilons. So we don't know. We don't know what happens. Well, remember that we always know about the divergence field. And the del dot D, no matter what, is just equal to the free charge divided by epsilon naught. Free charge is charge that's not bound to anything. Well, any charges here are going to be bound to that dielectric, so they're not free. So that we know in this region that the free charge is 0. So because there are no free charges, because there are no free charges, because when the university charges you, it sure isn't free. All right. So there are no free charges. We know that the divergence field, the normal, is continuous at the boundary. Well, all right, so then we got to go back and say, well, I know how to get E from the potential. How do I get D from the potential? So I go ahead and look at the definition that we have. The divergence field is equal to epsilon multiplied by E field. So the D is equal to epsilon E. So all I have to do is to take the epsilon and multiply it by this, or epsilon multiplied by minus the gradient of the potential. In other words, the negative gradient of the potential, that's the E field multiplied by epsilon. So inside, so my potential inside, I have to multiply by epsilon here. taking a normal component, so therefore the radial component. That must equal minus epsilon naught outside and evaluate that. All right, so let's do it. All right, so we want to take the derivative of this with respect to r. So I get minus epsilon multiplied by the sum, L equals 0 to infinity. I can pull this other stuff out. AL, PL. By the way, I'm just going to shorthand this PL. Just remember it's PL cosine theta. I'll write that out for you later. I want to take the derivative of r to the L. What do I get with respect to r?
LRL minus 1.
Yep. So I get an L, R to the L minus 1. Okay? That's it. So then we're going to end up evaluating that at r equals a. That's the equal. All right, let's do the other side. I take the derivative of this with respect to r. That r drops out. So in other words, that's just a constant times r. So I get this. So I get this first term, I get minus E naught cos theta. And then I come over here. I need to take a derivative of this. So I have plus some L equals 0 to infinity. Of CL, PL, and now I'm taking a derivative of this. So R to the negative L plus 1. So I get a negative L plus, oh, gee. Well, what can you do, right? So then I get a negative L plus 1 multiplied by R to the negative like that. I hope. Yep. Got a little confused there. And we're going to evaluate that at R equals A. I'm going to start just plugging in for A here, so get ready. All right, so A to the L minus 1. A to the negative L plus 2. Okay. All right, let me clean up a little bit. All right, so minus E sum L equals 0 to infinity. So what I get is I get AL, A to the L minus 1 times L times PL cosine theta. Now I'm writing this out for a purpose. Okay? Minus E naught. That is what? What is this? What is this? Which Legendre polynomial is that?
Sorry, which is what?
The cosine theta. I want to write that in terms of Legendre polynomials. What's cosine theta in terms of Legendre polynomials?
Just P1?
It's just P1. So this is P1. In fact, I'm going to highlight these. Here's PL. Cos theta. Here's P1 cos theta. Plus the rest of this stuff. L equals 0 infinity of CL. So minus sum L equals 0 infinity of CL negative CL times L plus 1 over A to the L plus 2 and then this is multiplied by my PL cos theta. And I forgot a term on this right-hand side. What did I forget on the right-hand side? I'm going to squeeze it in there. Because I put it over here. What needs to go over there? All right, Sebastian, I'm picking on you. Turn on your mic. You're going to answer this for me.
Trying to think.
Okay, here's the epsilon, right?
Mm-hmm.
I remembered this. What has to go over there? Let me give you a hint. It's not epsilon.
Epsilon not.
There you go. Squeeze this epsilon out here. So minus epsilon naught. And there's over here. Yeah. Epsilon naught. And there's epsilon. Make sure I get it. This has to be it. All right. Now we got it. All right, so since this has to be true, and this is what we do this all the time. That's why we pick to expand in these linearly independent functions, like these PLs and cosine theta, because I know that each coefficient, the coefficients of each PL must match up. So let's match up the L1 first. So we match up the L equals 1 term. Let's match up that one first. And so for that, we get this. Minus epsilon. A1. A to the 1 minus 1. What's A to the 1 minus 1? 1.
Just 1.
1. Because it's A to the 0, that's 1. So I'm going to write a 1 here. L, when L equals 1, is just 1. Okay? There we go. Now this has to equal minus epsilon naught E0. That's my coefficient of the P1 term there. And now let's get the coefficient of this P1 term. So this is going to be plus. Actually, it's going to be minus. Sorry, minus C1. 1 plus 1 is?
2. 2.
2. Times 2 divided by A to the L plus 2. So 1 plus 2 is?
3.
3. So it's A cubed. And this is times epsilon naught as well. Let's clean this up. So I get minus epsilon A1 equals minus epsilon naught E0 minus C1, I'm sorry, epsilon naught C1 times 2C1 over A cubed. And let's clean this up a little bit by dividing through by negative epsilon. So we're going to divide this through by negative epsilon. So I get A1 equals epsilon naught over epsilon E naught plus epsilon naught over epsilon times 2C1 over A cubed. Oh, darn, they did it the other way. Shoot. That's fine. All right, I'm going to take this. It doesn't matter. This is good enough here. So this is another one. Fine. What they did is instead of dividing, they divided by epsilon naught. So they got the epsilon over epsilon naught over here instead of this, but this is good. It's still legit. There we go. I'll write this down. Okay, so I gotta come over here. I gotta write this thing down. Actually, I'll rearrange it. So epsilon over epsilon naught times A1 must equal E naught plus 2 over A cubed C. Okay. So this actually can be combined with this right here. And then we know what the ones are. Okay? I'll do that in a bit. Let's go back over here. Let's rewrite this thing for L not equal to 1. So we're going to match the coefficients. We're going to eliminate this because there's no L equals 1. I'm going to divide through by negative epsilon naught. So what I'm going to get is I'm going to get epsilon over epsilon naught multiplied by A sub L multiplied by A to the L minus 1 multiplied by L must equal minus, no, there's no minus, I'm sorry. So I just left with CL times L plus 1 divided by A to the L plus 2. So did you guys get that? When we did that? Oh, sorry. Wait there. Oh, there should be. Let's get a negative there. Let's take the derivative. There's a negative there. Do the devil's one. All right. Let's take care of this. These terms. So let me check my algebra because no, that has to be right. We're getting a negative over there. There's negative of L plus 1. I'm sorry, I'm arguing with myself. So okay. All right, so let's take a look at this. I'm going to take this one here. So I'm going to actually start here with this. but I know right up here. So I also know from the other boundary condition that A sub L must equal C sub L divided by A to the 2L plus 1. Okay, so we know that. So I can just plug this in here and see what happens. Okay? So I got this number, epsilon over epsilon naught. I get C sub L here divided by A to the 2L plus 1. Oh dear. Well, I have a bit of a problem here, as you can maybe see from this, that no matter what I do, right, this coefficient, you know, for each L, right, must be equal to this coefficient for each L. But when I do this, the best I can do is to have something with this factor. Do you see what I mean? This factor right here, this epsilon over epsilon naught. Let's see, A to the 2L plus 1. So let me try to gather all these things together. So I got epsilon over epsilon naught CL A to the L minus 1 minus 2L minus 1. And I got to multiply that by L equals CL to L plus 1 divided by A to the 2L plus 1. No, L plus 2, sorry. L minus 2L is negative L minus 2. So this is minus L minus 2. Okay, so that's good at least, right? So minus L minus 2, which if I multiply both sides by A to the L plus 2, that gets rid of this. Okay, somewhere, and that gets rid of this. And so what we get is we get epsilon naught, epsilon over epsilon naught, L times CL equals CL times L plus 1. And so what we get is we get epsilon over epsilon naught equals L plus 1 over L. Nobody's reacting to that. You're half asleep again. I'm going back to my camera. All right, so let me kind of explain this to you. You see all this stuff that I did here? It doesn't work. None of it does. None of this works because it leads to contradiction. So in other words, this boundary, I can't solve this. There's no way to solve this for all the L's and all the angles. Because the things can't be true at the same time. So there's no way for this to be true and that to be true. So the only solution for any L not equal to 1 is pretty much the trivial solution, which you probably could have just guessed because of the fact that there's nothing here that would ever say that there's anything to do with L equal to anything more than 1. So for L not equal to 1, basically all the C's and all the A's would be what? Only one that works. Aha, Michael, you know what the answer is to be?
Oh, that's I pressed the wrong button. 0?
Yeah, that's be 0. Yeah, all these have to be 0. I know it was silly. I'm sorry I tried to actually solve this dumb thing. But what happens is you get an equation, you've oversolved for this thing. So they all drop out. All right. We're almost. All right, so we don't need any of this. There. This. The rest of it is some fun you can do on your own. To get the following numbers for A1 and C1. Okay. So you get A1 is negative 3/2 plus epsilon over epsilon naught times E naught. And C1 is epsilon over epsilon naught minus 1 divided by epsilon over epsilon naught plus 2 times A cubed. All right, let's take a break. Okay, so it's instructive for us to go ahead and just continue with this example, so I won't get to the second example. It's funny, one example takes an entire class period, but hey, what are you going to do, right? So now we erase all this back over here. So the only terms that we have are the A1 and the C1s, that's it. So what we finally get for the potentials, okay. We get the potential inside is equal to minus quantity 3 over epsilon naught plus 2 E naught R cos theta. And for phi out, we have minus E naught R cos theta plus epsilon over epsilon naught minus 1 divided by epsilon over epsilon naught plus 2 E naught A cubed over R squared cos theta. Okay, first I'm going to introduce a slight simplification. So if you ever remember way back when we defined the dielectric constant, so the dielectric constant kappa is equal to the electric permeability in the material divided by epsilon naught. So we're going to be nice and simple. In general, this could actually be some weird complex thing, but we're not worried about it. We'll just say it's a real number kappa. So that way we can just replace all these epsilons. This way I just don't have to write all this stuff. Okay. And for kappa equal 1, for kappa equal 1, that would be free space or a vacuum. And so notice what would happen. So if we put kappa equal to 1 in here, then this becomes just 1, and I just get the same field that I have outside. Kappa equal 1, all this stuff drops out. So that's good because if I put nothing there, then I should just get the electric field that I had in the first place. Yay. All right, so there's phi in, phi out. So what we want to look at now is we want to try to look at what's going on with the field inside and outside. So we'll take a look at the field inside. Well, the first thing I'm going to do here is I'm going to say, well, in this case, I want to change this up a little bit because this r cosine theta in Cartesian land, what's r cosine theta in Cartesian coordinates?
E.
That is z. There it is. Hooray. So this is just z, and this is just z here. Okay, so that's just z. Okay, there's more complicated stuff over there that we can't quite deal with, but it's just E naught z. So if we take the derivative of this in Cartesian coordinates, so we find that the inside, in terms of the electric field inside, okay, so E in, it's simpler to do this because it only has a z component. So if you just look at this inside, in other words, inside the sphere, our potential only is multiplied by z. Our electric field will only have a z component. So Ez. So this problem becomes Ez. See, it's easy. Oh, come on. Nobody's even laughing or grunting or anything. Come on. All right.
We were all laughing. We're just muted.
So it's minus d phi dz, which this minus gets rid of this. Take the derivative with respect to z, I just get this. And so, oh, look, it's just 3 over kappa plus 2 times E naught. Oh. So it's just a constant electric field inside the thing. So inside the thing, you get a constant electric field that's in the same direction as the electric field itself, as the original E. Okay. So you just, oh, okay, cool. Okay. So now that we know that this kappa is always going to be greater than 1, because you can't get more permeable than vacuum. Okay? So kappa is always greater than 1. This thing is always going to be less than the original E naught. So in other words, the dielectric has a way of, so the electric field in here, the actual electric field is slightly less than the electric field outside. So I guess I'll draw it like this. It's the same direction, but you get some shielding in here from the bigger electric field out here. Okay. So this is the overall electric field. So this is our picture kind of with the electric field. This is what's going on with the electric field. So what do we got outside the sphere? Let's take a look outside the sphere. Let's see what's going on. So that's what happened inside the sphere. Outside the sphere, we have this potential right here plus this stuff. All right, well, well, this is going to be the E naught z. So I'm just going to write this down. So the E out is going to be, this is just E naught in the z direction. Okay, E naught in the z direction, just our old electric field. Okay. So now let's figure out what happens to this thing. This thing's a little tricky because we want to see what the electric field looks like outside. Well, what does that look like? Well, let's see. Well, let's see what it looks like. The potential looks like, oh, I don't know. Wait a minute. If we go back, we've seen potentials with cos thetas over r squares, right? Have we seen potentials with cos thetas over r squares? I hope we have. I think it's a little tricky, but I think we have, right? Yeah, it's a little, they trick you a little bit with it. They do trick you because they put a dot x instead of a dot x hat or something like that. So, all right, so what happens is the outside is the original field plus this thing, which would be a field created by what's going on inside of the thing. And what's going on inside of the thing is that you have those little shifts, that shielding of the electric field. And so this is like a dipole. So this would be the same thing as a dipole, where you take the r cos theta, so you have a P, where the P is equal to this. So P is a little bit hard to see, so let me just show you. If you have the P, little p, the dipole, equal to this. Okay, 4 pi epsilon, let's go. 4 pi epsilon naught multiplied by this stuff. Multiplied by E naught. Okay. E naught A cubed. And we put that in the z direction. Okay, we're going to put that in the z direction. The reason why is because we need an r cubed down here. But we can do that if we say, oh, okay, when I put this in the z direction, I got an r cosine theta and then r cubed down here. See how that works? So I can do this. And then this becomes z over r cubed. And then I can turn this into stuff here. I'm looking back at equation 410. So I'm comparing this to this 1 over 4 pi epsilon naught p dot x vector divided by r cubed. So if my P is this, and I have that in the z direction, then this becomes z. So that's where I get that from. So this is just like a dipole at the origin. So that's what the outside looks like. It looks like I have the electric field, the original electric field, plus dipole at the origin. Somebody say hooray or something.
Hooray.
Yay.
Woohoo! Yay.
All right, so
When you were dying.
now I erased everything. So what I want to do is I want to look at how we do this in terms of the polarization quantities. In other words, if I took a look at the polarization, this capital P vector that we have. So remember that the capital P vector is our susceptibility E minus epsilon naught multiplied by the electric field, okay? Where the E is in whatever medium you're in. So in this case, the E on the inside, which I erased, okay? So I just multiply that by a factor of epsilon minus epsilon naught, and I get this. I get that this is equal to polarization capital P factor is 3 epsilon naught multiplied by kappa minus 1 divided by kappa plus 2 P naught. And that is in the Z direction. So when we look at what's going on inside of there, I said, okay, so this is kind of from, this is our overall perspective. Now let's kind of look at the two things, the two effects individually. So what we have is we have the electric field going on here on the outside. And now I have this polarization on the inside. So this is our polarization. We can calculate what we call the bound charge density, the charge density associated with the polarization. And there's two things that we do when we look at this. So remember, well, whether you remember or not, what we have is we have those equations that when we derive them, then we had this quantity minus del dot P. Okay? And this was the bound charge density. The bound charge density. The problem is if I look at this field, I would take the derivative of this with respect to Z. What is that? Well, let's see. The E naught is electric field. We already know what that is. Kappa is a constant, so is epsilon naught. Constant, constant, constant. Take the derivative of a constant. What is it?
0.
It's 0. Also, there's no bound charge density, which is fine. Because the polarization in here, the polarization is uniform inside of it. So now what I've done is I have a polarized sphere. So, but there's no non-uniformity. So there's no like volume charge density. However, when we look at the surface, there is a surface charge density because there's a discontinuity in the polarization. Because there is polarization inside, but there is no polarization outside. So if we look at the, so this is the rho bound. So rho bound is equal to this. Sigma bound is equal to minus P2 minus P1 dot normal. All right, ready for us to do this? All right, so let's get our P. All right, so the sigma bound is P2 minus P1. So what we're going to do is P2 is out here, P1 is in here. What's the polarization outside of the dielectric sphere?
Zero.
It's 0. There's nothing out there. There's nothing that can be polarized out there. It's vacuum. So this P2 is equal to 0. It's equal to 0. The normal to the surface is in the r hat direction. So unfortunately, we have to go back and we have to change this again. We have to put this in terms of our polarization. We have to put it in terms of r. And so this is So instead of the Z, so the polarization here is like, okay. So then this is R hat. So we're going to change that to P dot R over R. This is minus minus, so this is 0. So this is equal to positive P dot R hat. And so when I put the Z hat dot R hat, what do I get? So it's equal to stuff. What is that? That's a Z, by the way. Somebody should remember. If I have a dot product with two things at one, so remember, A dot A, right, dot B, we're going to go all the way back, okay? Is equal to A, B times what?
The cosine of the angle between them.
The cosine of the angle between it. Oh, good. Okay, where theta is the angle between A and B. All right, so here's the dot product here. What's the magnitude of R hat? What's the magnitude of any hat vector? Any hat.
1.
1, because the hat makes it a unit vector. So by definition, a unit vector is 1. So that's 1 and 1. What's the cosine? What's the angle between R, this is Z hat, and this is wherever your R hat is. What's the angle between them? What do we call that? What do we call the angle between the Z and the R?
Theta.
It's theta. That's our theta. That's our coordinate theta. Okay? So this is just cosine theta. Okay? So if we look at what the charges are doing inside, this bound charge is doing, is we see that it is positive where the theta is. So in other words, this is our positive z-axis going up here like this. We get positive charges built up here, and then no charges here, and then negatives on the other side. So what's going on with what's going on inside is that these bound charges from the polarization kind of create their own little counter electric field. Now, there are a couple of things that we can look at. If we take a limit as kappa goes to 0, I'm sorry, kappa goes to 1, then this basically becomes that there's no real distribution here because kappa goes to 1. Whoops, I'm sorry. Sorry. It's minus. There we go. So as kappa goes to 1, there is no charge density. But there's another extreme that we can take. And we can say, well, what happens if this happens? Let's say that kappa goes to infinity. Say that kappa went to the infinity. Okay? I want you to call the electric field in there looks like this. So the electric field inside was this. It goes 3 over kappa. 3 over kappa plus 2 times epsilon times E naught. Sorry. So this is the electric field inside. And here's our polarization. So if kappa goes to infinity, so as kappa goes to infinity, that's another limit we can take on these dielectric things. Okay, as kappa goes to infinity, oh man, I'm glad the semester's almost over. My pens are dying. As kappa goes to infinity, what happens to this number? What's the limit of that thing as kappa goes to infinity?
Goes to 0.
No, because this is kappa over kappa. So in other words, your leading terms here are kappa over kappa. So as kappa goes to infinity, this thing would go to
Yeah,
what?
it's infinity minus 1 over infinity plus 2. I think the plus 2
Yeah,
it weighs out.
So infinity minus 1 divided by infinity plus 2.
Does it just sort of go
It's
approximate?
just 1. So this part's just 1. So when we get here is we go, oh, okay. So the sigma becomes 3 epsilon naught E naught cos theta. Okay? That's what happens if kappa goes to infinity. What happens to the electric field if kappa goes to infinity? We look at the electric field now, inside. What happens? If kappa goes to infinity. Well, here we have nothing divided by kappa. As kappa goes to infinity, what happens to the electric field? Oh man, you guys are tired. Hang on. I'll try again. Electric field equals 3 divided by kappa plus 2, right? Times epsilon naught. It's the electric field inside of the dielectric, right? All right, E divided by kappa plus 2. When kappa goes to infinity, what happens to this? Chris, what happens to it?
0.
It goes to 0. This goes to 0.
I was gonna answer.
Okay, so we look at our kappa equals 1 as being a vacuum. What would kappa equals infinity best represent? Let me give you a hint. The electric field goes to 0.
Wait, can you say that again?
Perfect insulator.
So
Oh.
what we said is that kappa equal to 1, that represents a vacuum. What I'm asking here is, if we take the limit of kappa going to infinity, what kind of objects do those represent in terms of electrostatics? And the thing that happens is the electric field will always go to 0. Should always go to 0 inside of something where kappa goes to infinity.
Okay.
Is that a perfect insulator?
Other way. The opposite. Opposite of the insulator
Conductor?
is a conductor. Because remember, in your conductors, you can't put an electric field inside. Because the charge will line up, will always move until the electric field is 0. So the dielectric is kind of a middle point between. Some of the charges can move. The charges can rearrange. I mean, they can't like leave, and they can't just go wherever they want, like a conductor. But some of them can move. They can shift around. So it's kind of a partial shielding. All right, so I think we've had enough fun in this chapter. Yay. All right, so on Wednesday, we'll start into chapter 5. Great. All right.
I'm excited.
Yay. Okay, that's it. Enjoy yourselves.
All right.
Bye.
Have a good night.
Mm-hmm.